Welcome to your Algebra 2 Lesson 2.1 on representing relations and functions. So your objective today is that you will represent relations and graph linear functions. Representing relations can be done in several different ways. You can list ordered pairs. Okay, so you see there's a list of ordered pairs and the corresponding points that are represented by the ordered pairs can be written in a table. So here we have an XY table, and so the X values are listed and their corresponding Y value. You can graph by plotting the points. Notice the points aren't connected or anything, it's just the plot of the points themselves. And then kind of an interesting way to do it is with a mapping diagram, where the X values are put as a set of inputs and the Y values are listed as a set of outputs. And then you can follow the arrow and see what each input maps onto. So here you can see that -2 maps onto -2 as well as +2. And if you look over here, sure enough, -2, 2, -2, -2 are points. Okay, and so 0 maps onto 1 and so does 3 because 0, 1 and 3, 1 are also points or ordered pairs represented by this relation. Okay, so we're going to consider the relation given by the ordered pairs. There's more than one, it should be ordered pairs. -2, -3, -1, 1, 1, 3, 2, -2, and 3, 1. We're going to identify the domain and range. And so the domain, if you'll recall, consists of all the x coordinates, so -2, -1, 1, 2, and 3. And the range consists of all the y coordinates, so -3, -2, 1, and 3. Now there's another 1, but we already have it listed, so when we're writing out the range or if we're writing out the domain, if there's a repeat, we don't have to list it twice. We're going to represent the relation using a graph and a mapping diagram. So for a graph, you just plot each point, and y'all know how to do that. So here's the point 1, 3, and the point 3, 1, and then -1, 1, and so on. You just plot the different points. And then finally, to do the mapping diagram, you list all of your inputs, and then you show how each input maps onto the different outputs. So from this, we can tell that -2, -3 is a point in our relation. -1, 1 is a point in our relation. 1, 3 is a point in our relation. 2, -2 is a point in our relation. 3, 1 is a point in our relation. So what is a function? What makes a relation a function? Okay, a function is a special type of relation, and it's a type of relation for which each input has exactly one output. So on mapping diagrams, each input is only going to have one arrow going out from it. Okay, so this is a function. If any input of a relation has more than one output, the relation is not a function. So we're going to tell whether the relation is a function, and we're going to explain. Okay, so here we've got our inputs and we've got our outputs. So -3 maps onto 2, -1 maps onto 3, 2 maps onto -4, 4 maps onto -4. Now, there are 2 arrows pointing at -4, but that's okay. What we're looking for is that there's not 2 arrows coming from any one input. So this is a function because each input is mapped on to exactly one output. Now let's look at this one. -2 maps onto -4, but 1 maps onto -1 and +2. So that's a problem. You've got 2 arrows coming out from a single input, so this is not a function. The relation is not a function because the input 1 is mapped onto both -1 and 2. So if you look at the same relations and you put them on the graph, you can apply what's called the vertical line test. A relation is a function if and only if no vertical line intersects the graph of the relation at more than one point. So any vertical line is either going to hit the relation one time or not at all. So if we look here, an upward opening parabola here, anywhere we draw a vertical line, it's going to hit our function exactly one time. That means for every x value, for every input, there's only one y value, only one output. Over here, this right opening parabola, a horizontal parabola, is not a function because certainly right here, right here, right here, in all kinds of places you can draw a vertical line going straight up and down, and it's going to hit more than one point. Okay, it's going to hit a couple of points. And that's because, for instance, the x value 1 has a y value that corresponds to it up here, has an output up here, and it has a y value down here, an output down here. So the vertical line test works for us because if a graph of a relation fails the vertical line test, that means that for at least one x input, there are at least two y outputs. So we're going to use the vertical line test in a basketball example. The first graph below plots average points per game versus age at the end of the 2003-2004 NBA regular season for the 8 members of the Minnesota Timberwolves with the highest averages. The second graph plots average points per game versus age for one team member, Kevin Garnett, over his first 9 seasons. Are the functions shown by the graph, or the relations shown by the graph's functions? Explain. So we're going to be applying that vertical line test. So here are the results for Timberwolves. We've got age in years, and then we've got average points. So let's see, for 27 years, there's only one output. There's only one average point. But oops, look here. For 28 years, you've got a point here and a point here. So this fails the vertical line test. You've got 2 different outputs, 2 different average points for the same input, age and years. But if we look at Kevin Garnett's, here we've got his age per year and average point. You can see there's only one output for each input for each age. So the team graph does not represent a function because vertical lines at x equals 28, and if you look right here at x equals 29, these 2 points are kind of hard to see, but there are 2 different points there. Each at x equals 28 and x equals 29, each intersect the graph at more than one point. The graph for Kevin Garnett does represent a function because no vertical line intersects the graph at more than one point. Okay, we're going to graph an equation in 2 variables. We're going to graph y equals negative 2x minus 1. Now, in the future, we'll be talking about all kinds of ways to graph lines, but I want to talk about the most basic way to graph any equation in 2 variables. You can always select inputs, select x values, and generate outputs, generate y values. You can always do that. So that's what we're going to do here. We're going to construct a table of values. Now it can be horizontal like this one, or it can be vertical like the ones you saw earlier. It doesn't matter. But you just pick out x values. Now I suggest doing a couple of negative, do 0, and do a couple of positive. Now how do we get the y values? The y values are generated by the equation. So I plug in negative 2 for x, and so negative 2 times negative 2 is 4, minus 1 gives me 3. If I do negative 1, negative 2 times negative 1 is 2, minus 1 is 1. I plug in 0, negative 2 times 0 is 0, minus 1 is negative 1, and so on. And then we simply plot the ordered pairs. So plot the points. You'll notice they all lie on a line. And you're going to connect the points with a line, and you end up with a nice linear function. Okay, again, I've been calling it a linear function because it fits in the correct form. Linear functions can be written in the form using xy notation, y equals mx plus b. Or if you're using function notation, remember f of x means exactly the same thing as y. F of x equals mx plus b. If a function cannot be written in one of these 2 forms, then it is not linear. Alright, so we want to tell whether the given function is linear and then evaluate the function when x equals negative 4. So we're going to evaluate whether the function is linear or not, but first we're going to identify whether it's linear or not. Okay, f of x equals negative x squared minus 2x plus 7. If we didn't have that x squared term, we'd be good to go, but that negative x squared term means that this is actually quadratic. It's not linear. The function f is not linear because it has an x squared term, but we're still going to evaluate it when x equals -4. So we're going to write the function. Notice that we've made the x in red. Everywhere you see an x, conveniently in red for you here, we're going to plug in -4. So we're going to have f of -4 equals -4 quantity squared minus 2 times -4 plus 7. So we're going to simplify. So let's see, the -4 squared is 16, but with that negative, it's -16. This will become plus 8 plus 7, so that's -16 plus 8 is -8 plus 7 is -1. So f of -4 is -1. All right, let's look at part B. G of x equals 5x plus 8. That is in the correct form because it has the form g of x equals mx plus b. So yes, it is linear. Now we're going to write our function again. Notice we've put the x in red just to make it really clear where we're substituting. We're going to substitute in -4 for x. So g of -4 is equal to 5 times -4 plus 8. So that's -20 plus 8, and so that's -12. So g of -4 is -12. Okay, guys, that's it for your examples. Do the problems to try on your own. Remember, those have to be done to get full credit for your notes. So you want to get that credit, so do those problems to try on your own. I'll see you in class. Have a good day.